Hello. Wow, Katie's in a strobe light. Okay, hello, 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 hello. Good afternoon. Hello, hello. Okay. Okay. Well, hello, Josephine. Hello, Maria. Thank you, Maria, for being here for a long time in the waiting room for your patients. Okay, thank you. Hello, good afternoon, Alexis. Hello, Josephine. Good afternoon, Shirley. Good afternoon, Emily. Good afternoon, Katie. Wait, where did Katie go? Okay, yeah. Good afternoon, Maria again. Good afternoon, Victoria. Good afternoon, Paulina. Good afternoon, Claudia. Afternoon, Eric. Okay, or unmodified afternoon. Okay, let's get we're just gonna get going. It's that time of year. We're just gonna get going. Good afternoon, Logan. Sorry. Yes, excellent. Okay. And what? Oh, and here comes. Okay. And one thing, super quick. I really appreciate. The I did an experiment this year where I put and good afternoon. Sorry, who was that? Oh, good afternoon, Brandon. Okay, excellent. Yes, good afternoon, Jenna. Excellent, excellent. Good afternoon. Okay. I so thank you very much. Many of you have done the course evaluations, and I only know that because you and I was going to give time to do them today, but I really appreciate that so many of you have done them. I definitely I put the link in like under homework in the Google Classroom just so that you'd have the link and to encourage you to do it. But that was like a weird thing for me to do. I mean, obviously, I have not seen and I will not see your course evaluations. I mean, some of you even screenshot just to prove that you did it, which I totally appreciate. I did not mean for it to be like that kind of thing. Like I can't give you points. Maybe I guess I could give you points for having done them. I'll think about that, but I never meant for it to be a thing of that nature. I just wanted to put the link. Anyway, I wanted to put the link somewhere where you definitely have it. I've never sort of put them in the homework portal before, but it seems to have had the effect that many of you have done them. So thank you for that. Whatever you said, I do not know. I will not know. Certainly not like on an individual basis or a name basis. So I apologize for the awkwardness of having put them there. But because so many of you did them, if you haven't done one, please do. If I can at the end of this class, I will. That's what I will try to do. I will try to cut things off like 15 minutes before the end of class today so that those of you who haven't done it can have the proper appropriate time that you need to do them, which I should do. And those of you who have done them already, like you can go early because thank you. Anyway, but I realize now it was sort of awkward that I put them in when I saw that so many people actually responded and screenshotted. That was like so nice of you, but then it made me realize, okay, I shouldn't have done that really. Anyway, all right. So thank you. And if you want to remind me, like someone wants to remind me, like, let's say 20 minutes before the end of class, I won't stop right on a dime, but if you remind me 20 minutes before the end of class, I'll like wrap up. And that way, those of you who can do them then, that would be great. And those of you who have already done them, you can leave early. So that's the best thing I can say. Anyway, all right. So, and good afternoon, Jenna, if I didn't say so. Okay. That's a long way of saying thank you. Okay. All right. Let's get to the material. And it's still, and thank you, those of you who did this homework so quickly. And those of you who didn't, I will still accept old homework assignments for another week. Not old daily game turns. That's the only thing that doesn't make sense to give me within the next week. Like, don't please give me game turn number 1 or 2 or something like that from weeks ago. I hope that makes sense what I'm saying. Like, not the 5-point game turns. Those don't. But other than that, I'll accept old things for a week. Okay. And having said all that, I'm going to get straight to going over this last homework that we had. There's certainly no more, for what it's worth. It's not clear. There's no new homework assignments for the rest of the semester. That's for sure. The one summary of what. Oh, good question. Okay, because I was about to say anyway. Yeah. IE after it says. Oh, yeah, that is hard to read actually. Oh, okay. Right. Someone's asking about my handwriting on this board. I was about to read it anyway. Let me fix the handwriting and then I'll read it because you're right. It is illegible. It says, Okay, what it's trying to say on this board here, in English, it's trying to say, i.e., work transfers energy. That is the point. That is the point that we want to be investigating right now. Couple of quick summaries of what that means. So that's English, right? Work transfers energy. Let me like summarize that or expand on that actually, and then we're going to apply it to the homework that was assigned. Okay, the left side of the equation on the board here, the left side is the meaning of work itself. So you could say, someone's here, sorry. You could, like, I don't want to remember, there's a big difference between triple equal signs and double equal signs. So you can say, I guess, like, I'm not changing this. Like, what we spent like a day and a half trying to develop is that what work is by definition is this. Okay, this is a calculus concept, right? As we said, like in English, what we're saying is work is defined to be the path integral of force. Okay, that is what work is, and a path integral means an integral of a dot product. Okay, like of a dot product with respect to space. Like, no joke. Well, why would that be a joke? It wouldn't be funny. But I mean, and again, okay, like in general in math, a path integral of some dependent variable, say z, if I say the path integral of z, what I really mean is the integral of z vector dot dx vector. Like, I'll say that one more time. In gen, because it'll come up again in physics 204 and like in life, depending on what you do in your life. If I refer to the path integral of some variable such as z, what I mean is the integral of z vector dot dx vector. And to be even more specific, really, usually when I say path integral, I mean the definite integral. So I would mean like the integral from x1 to x2 of z vector dot dx vector. Now, what does that mean in English? And so in this case, when I say that work is the path integral of force, I mean, like just what it says on the board, that it's the integral from position x1 to position x2 of the force vector dotted with displacement vector. Okay, so what we're really saying in English, when we say path integral of force, when we say that work is the path integral of force, we're really saying it is what you get, what you compute, what you total up, what you find when you walk along a path, and each infinitesimal step you take along that path, you ask how much the force is acting and in what direction, and you multiply that force vector with the little bit of step that you took along the path. Like, you multiply the newtons of that force vector with the meters of the infinitesimal step that you just took. You multiply them together and you add up all those products all the way till you get to the end of the path. And that continuous sum of infinitesimal products of force by displacement is what we mean by work. And when we say that it's a dot, when we say that every time you multiply the force by the displacement that you're doing a dot product, what we're really saying is, again, I'm saying this quickly because this is technically like what we already explained last week, that dot between the two vectors signifies that we're really only multiplying the components of those two vectors which are parallel to each other. We're taking two vectors that could be pointing in any direction at all. And then we're only multiplying the component of one vector, which is parallel to the other vector. So and thereby the answer we're getting is just a number on a number line. It's a scalar result, right? So we're ultimately to calculate work is to calculate how much a force acted in parallel along with a displacement along some total displacement, like that, right? That's what work is. So that's what work is. And that's what we've been saying for the last week. It's like the accumulated effect or consequence of force acting throughout some region of one-dimensional space. That's what work is. The reason we care about it now, we're saying, the reason we care about it, like what it does, the sum total of work when acting on some object, i.e. the work done on some object from any number of various forces that might be acting on the object. In other words, the net work done on an object by virtue of the net force acting on an object. What we're saying the consequence of that is that changes the 1/2 mv squared of the object. Please note again that all of last week, what we were developing was the triple equal sign meaning of work. But then this statement that I just wrote at the top of the board is the double equal sign consequence or impact, whatever, result of work. Right? This is what work does. And what does it do? It changes the 1/2 mv squared of an object by transferring 1/2 mv squared to it. Okay, okay. So I'm expanding now on what I mean by when I say transfer. I'm saying just mathematically, if you just look at that, the sum of work on some m brings the 1/2 mv squared of that m from some old value to some new. Now, again, I'm telling you, when I write that statement down, when I derived it algebraically last week, I just derived it algebraically. I'm not making an assumption that you already had any reason to care about 1/2 mv squared. Like you might have seen 1/2 mv squared in some prior science class or prior high school physics class or whatever. But this, and that's great if you have a comfort with it. But I'm, as far as I'm concerned, I'm introducing it for the first time as a concept here. I'm just saying, if you just do the algebra of what happens when you apply force through some distance, it turns out that the algebra just says that whatever object you were pushing or pulling through a distance, it has this combination of measurements that changes as a package. Like we just find that out, that this package of measurements, 1/2 the mass times the square of the speed, is what gets changed when you do work, net work on something. So therefore, from here on in, we start tracking that combination of measurements, the 1/2 mass times square speed of something. From here on in, we track that because it's what goes from an old value to a new value every time you do work. And like literally, like, well, yeah. So we give it a name because we're going to track it from now on. We could call it the 1/2 mass square speed. Literally, no joke. Like we could just call it the 1/2 mass square speed of an object. And then we would call, but that's like awkward. And it turns out to be so important, this package of constants, because this package of measurements, because again, this is the package that gets altered when you do work on something. And when I keep saying that this package gets altered, gets changed when you do, I literally mean like if you do 3 joules of positive work on a sled in order to pull the sled from position 1 to position 2, if you do 3 joules of work on the sled, what I'm saying is it's 1/2 mass times square speed will go up by exactly 3 joules. Like that's what I'm saying. Its speed won't go up by 3 meters per second. Its mass won't go up by 3 kilograms. It's not that simple. But if you were to write down its mass, divide by 2, multiply it by the square of its speed, write that whole number down. First of all, if you looked at the units closely, you notice that the units of that whole package is joules. It is newtons times meters, or specifically, it's kilogram meter per second squared times meters. And if you think about it, that's the same thing as newtons times meters. So if you wrote down, before you did work on this sled, if you wrote down the speed, and you squared it, and you multiplied that by half of the mass, and you got a number, that number would be measured in joules. And then you do work on the sled, I'm saying the number of joules that is its half mass square speed would go up by exactly the 3 joules of work that you did. Like that's what this algebra says. So we start calling that quantity. We call that quantity the kinetic energy of an object. Okay? If nothing else from all this, if you want to memorize that the kinetic energy of an object in physics, in classical physics, is always 1/2 mass times square speed, you can memorize that. Like that's reliable. That is true. And that's a minor takeaway of what I'm saying now. From here on in, we call the kinetic energy, from here on in, we call 1/2 the mass times the square of the speed of an object its kinetic energy. But the thing that now I'm trying to say is, the reason I'm using the word transfer, I'm saying that if one object does positive, well,
did you say that that equation was the equation for net work?
oh, great question.
Because I just was wondering, there was like a couple problems or like parts on the homework where it asks to find the net work, and I just added up like the work values that I had found.
Right. Wait, very good. Good question. And you didn't do, I mean, if I'm remembering, if we're talking about the same like things on the homework, I don't think
Yeah.
I don't think you made a mistake. Agreed. Okay, good, Shawnee. I don't think you made a mistake. Let me clarify. Like in order to calculate the work done, in order to calculate the net work done on an object, yes, it would be the sum of all of the works done on that object. Right. Like all of the F times X's on an object. Yes. But then when I'm saying, if anybody then ever asks you anything about energy, or more specifically, and this is what I'm getting to now, if anybody then asks you to predict anything about energy, or more specifically speed, you use your network. Okay, it looks like you're nodding. Good. Okay.
Yeah, that's what I did. But that's what I was confused, because that's like exactly what I did for the first 2 homework problems. So the boulder going up and the boulder going down is like, it asks for the net force, and you just kind of add the sum of the forces that you found previously. And then in the next like parts, it would ask for like how much energy or something had, or like what the speed was. And I used that equation with the net force.
Yeah, no, so I think you're exactly right. And this is all the more, and I'm glad you're saying this, and I'm glad other people are like supporting you. All this tells me that I should get even more quickly to just going over the homework. And I will in a second. I'll just summarize the sentence. But yes, what Josephine is saying, everybody, like this is exactly what I mean by the difference between a triple equal sign and a double equal sign. Like, yeah, to compute, to know what the net force is, to know what the net work is, you add up all the works. Yes, or you add up all the forces and you multiply by displacement. Same point. The net work is the force times the displacement. But then the reason we care is, once we know that quantity, then the point of it is that it transfers energy, and energy tells us about speed, which we ultimately care about. So yeah, I mean, yes, Josephine is right, number 1. Number 2, that's a helpful like clarification. Number 3, yes, I should just pretty much get to the homework and show you this concretely. But I think the summary that I'm trying to tell everybody right now, or the one thing I want to make clear is, it's not that work equals energy. Not that Josephine is saying this at all. She's not. But to everybody, it can be easy sometimes. Work is not energy. Work is transfer of energy, i.e., When what I was just going to write, I'll just write this and then we'll go to the homework. If one mass does positive work or positive net work on another mass, I'll even be more specific. If one mass does positive work on a second mass, then the second mass gains an amount of kinetic energy precisely equal to the work done, to the net work done. And here's my point, just to be clear, and the first mass loses this KE. In other words, this is what I mean by transfer, just to be clear. When you do work on literally, and I would write this down. I'm not going to write it down because I want to make sure I get to the homework like that Josephine's asking, but I would write the following down. Like, work is to kinetic energy as economic transactions are to money. Like, literally, work is not literally, analogously, work is the transaction. Kinetic energy is the money. Work is what one object does to another. Kinetic energy is the commodity that's being passed, transferred, sent from one object to another. And it is like a zero-sum game. Oh, I'm going to look in the chat in a second. I'm not sure if I'll look in the chat in a second, right? Like, literally, if I do 5 joules of work on you, you gain 5 joules of kinetic energy. And where did it come from? From me. I therefore lose 5 joules of kinetic energy. And if I do 5 joules of negative work on you, okay, then I'm grabbing energy from you. So I would gain 5 joules of energy and you would lose 5 joules of kinetic energy. It's like, so we think of energy from now on as like a ball, it's like a thing, a commodity. It's not material, but that we're passing around. How do we pass it? By doing work. By the way, then you could even ask, well, what's the point of it? Like, who cares? Like, what? Well, and you could write this down too. I'm trying to go quick again, because I'd rather satisfy what you're asking than just like do what's in my head. But work is the transfer of energy, of kinetic energy. What is kinetic energy? Well, kinetic energy is the ability to do work. It is a circle. I'm going to say it one more time. Work is the transfer of kinetic energy. Now, I mean, that's not what it is, right? But that's what it does. What it is the path integral of force. But what work does is it transfers energy. What's the point of energy? Energy is the ability to do work. Is that circular reasoning? Well, yes, but only to the extent that anything you ever say about money is circular reasoning. What is money? Money is the ability to spend money right? Like, why do I want money? Well, if I did, I'd be in a no. Why do I want money? Because I want the ability to give it to you in exchange for like a car or, an apartment or the clothing, whatever, right? The more money I have, the more I have the ability to enter into a transaction and pass that money over to somebody else. Now, obviously, in exchange for something of presumably equal value of a different form, right? Presumably, I give you money for something that I give you $100 for something that's of $100 in value, but is some other form, like a Pokemon deck or something, right? Same thing with energy. Energy is the ability to literally what energy is. If you're a big object moving really fast, you have the ability to crash into, to come into contact with, to interact with another object and push it and pull it so that it now is going fast and you're going slower. Your kinetic energy, your bigness and your fastness is your ability to interact with another object and thereby get it going faster. Now, why would we? That's it, right? It's a circle. The faster I'm going, the more I can make other things go fast. Why would we ever want to do that? Because it turns out that energy can come into different forms, as you know. When we go into enter in these work transactions, these transfers of energy, it turns out that we can also then convert energy into like a thermal form and, heat up a slice of bread and call it toast. Or we could turn the energy into electromagnetic radiative form and like light a light bulb, or all of which we get into in physics 204. But that's what it is energy, work is the transfer of energy. Energy is the ability to do work. And so from here on in, we think of energy as the commodity and we think of work as the transaction. So I'm going to start applying, and the whole purpose of the whole thing is to predict how fast things are going at various positions of space. I'm going to say that one more time, then I'm going to turn to the chat and turn to the homework. But the purpose of the whole thing, at least this whole construct of work and kinetic energy, the purpose is to be able to predict how fast objects are going at various points in space. You might say, I'll say that one more time. The purpose of this is to predict how fast objects are going at various points in space. If it slightly occurs to you to think, wait, don't we already have that? Like, don't we have a million equations for velocity and acceleration and all that? Yes, in a way we do, but all the equations and all the concepts we have to this moment are all as a function of time. This is now where we're looking at how things vary as a function of space. We're shifting our focus to making space the independent variable. That's a big, it's not the whole only reason, but that's a big part of like what's happening now is we're developing a one-to-one correspondence between instantaneous speed and points of space rather than points of time. Okay, but that's a big picture. I'm about to go to the homework now because that's like the right thing to do. But let me just look in the chat. I might have already addressed the chat. I'm not sure. Okay, wait. I believe either works depending on what values. Oh, yeah. So Alexis's thing. I'm sorry. Yeah, absolutely. By end of the day, equations are equations. Whatever you use, whatever equation will work depending on what values you have. Yes, I mean Alexis is definitely right. A good observation for sure. So yeah, I'll leave it at that. Yeah. I mean, if you have certain values and your equation applies to the values you have, yeah, good, like, yes. So yeah, good point. So all right, so I'll go to the homework. I'll try to go, hold on, just pull it up. Okay. And I think I'll go in order. So, all right, I keep forgetting, this is homework 9, I think. Okay. And I'm gonna do this. I'm not gonna write out every single step. This is more like okay. Just to be clear, like what I'm giving you here is answers and maybe some thoughts, but I'm not giving you full solutions, which is all that So you got to do full solutions if you're turning it in for points or if you're using this as a model for what you would do on an exam. But okay. But you understand. Okay, so, but I will draw the diagram so we can know what I'm talking about. Okay. So for the first one, so this is boulder rolls down. And the first question is calculate the work done by gravity on the boulder as it travels down the ramp. Okay, is this work negative or positive? Okay. Before we go any further, okay, this is a good question. Hold on, I'm just going back to the screen. Okay. First of all, we've gotten in the habit, we should always label a coordinate system before we go any further. This ball is just going to is rolling down. It's never going up. So I'm going to call down positive. I'm going to call up negative. Similarly, I'm going to call right positive. I'm going to call left negative. You know what I mean, right? I mean, if my coordinate system is horizontal, vertical, I'm not even sure it will be, but okay, I'm calling the direction it's going positive. Now, and I'll tell you in advance, that no matter how you label your coordinate, I'm going to say this right now, no matter how you do the math, and no matter how you label your coordinate system, the work done, I guess I'm skipping a quick, I will do it, but the work done by gravity on this ball is definitely positive. I think that was one of the questions, right? I will. Oh, okay. Yeah, it is. I'm going to do the math, of course, right now. But I want to make it clear before I go any further. I don't care. I do care that you label your coordinate systems. But please note, no matter what we're saying, gravity's pulling this thing down and this thing is rolling down. I mean, it is going in the. So once you set up the math and you do cosine of theta, like theta is not 180 degrees. Theta is more like 0 degrees, depending on how you do it. I'm just saying that gravity is in agreement with the direction of the displacement. So even if you call the downward direction negative, then that's negative both for the force of gravity and for the direction of displacement. So gravity is accomplishing its mission. It is definitely doing positive work. And therefore, the ball is gaining kinetic energy. It's going to be getting faster and faster, as you know. So just remember, so that's just like a foreshadow, but work is a product, a dot product of force times displacement. So a positive times a positive is a negative, just like a negative times a negative is a positive. Sorry, a positive times a positive is a positive, just like a negative times a negative is a positive. Okay, so the work done is going to be positive, but what is the work done? All right, that's the real question. So I'm going to go on the next page. Now we got two choices here. If we're trying to stick with what we learned in the lab and all of that, I'm going to say my first instinct as a physics student, I'm going to choose a coordinate system that, well, I mean, here's the free body diagram, right? The free body diagram is that mg is pointing down, the normal force is pointing to an angle like that, and there's no friction or anything like that in this problem. So that's like the whole free body diagram, right? So something has to be, and I have to analyze forces because work is, work is force times displacement. So I have to look at forces. I'm going to do the same thing I did in the lab, at least in my approach number one. I'm going to tilt my coordinate system like we did in the lab. And therefore, I'm going to say, to cut to the chase, and you can stop me, I'm assuming that this is sort of clear now from the lab and from 2 weeks ago and everything, but it seems to me if I tilt the coordinate system, I then break up gravity, right? Like normal is still like this, but gravity is like this. Right? So the work done by the force of gravity that is relevant to displacement is mg sine theta. So I'm going to do the dot product of mg sine theta with the displacement. But even before I get into that dot product, well, yeah, okay, I will. So the F that's relevant here is mg times sine theta. Well, here, let me be. Actually, wait, sorry. Let me do one thing to make this easier before I do that. I'm about to put in the vectors to do the dot product, right? But some of us might still be intimidated by the integral sign or not know what to do with the integral sign or what. And ultimately, the integral sign does become very important. But in this case, as the homework says, we're calculating the work done by a constant force. That is to say that F is not varying as a function of dx. The F is the gravity, no matter how complicated it might be to look at, the gravity is not changing from one place to another. The whole reason we need integrals is to acknowledge or to take care of situations where the force is changing from one position to another. But that's not happening here. In other words, no matter how you feel about integrals at this point, one thing that many of you might know is that I think one thing that you know about integrals is if f is constant with respect to dx, then it comes out of the integral, so to speak. Right? In other words, in this case, here f is constant. So here we don't actually have to worry about the calculus as such. We can go like this. That's sort of important. That's going to happen a lot in the homework, so I'm only going to do it once right now. But it doesn't happen all the time in life, but it happens in this homework because we're told that the force is constant. Okay. And the fact that constants come out of integrals like this, I know many of you know this from calculus class. I don't know if it's clear to you why or not, but if you really get into your mind that an integral is a continuous sum, right? That the integral of f with respect to dx really means f1 times dx plus f2 times dx plus f3 times dx, et cetera, et cetera, et cetera. Well, so it's like what we're doing is doing a long summation of a bunch of products. If the f in all of those products is one and the same number, it's what we're just doing is factoring that f out. We're just saying, oh, it's f times dx plus f times dx plus f times dx plus f times. So you just factor the f out and you have one f times the sum of all the dx's. And the sum of all the dx's is just x. I don't know if that helped anybody, but the reason we can take a constant out of an integral is because we're just factoring out the value from a whole big string, a whole big sum of products. And we can do that if and only if there's one value that is the same throughout all those products. Anyway, all right, for whatever it's worth. So I'm now saying our work here in this case, our work is just the dot product of f times x. Well, wait, sorry. F times x. Okay. So, and that means the dot product of f times x means the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. Okay, so here f is mg sine theta. Okay, like that's the force along the plane. What is x? Well, if x means the displacement along the plane, right? If we're trying, if we're trying to match a component of force that is parallel to displacement, if we want cosine of theta to be 1, right? And that's the whole point of the cosine theta thing, is you're supposed to multiply a component of force that is parallel to displacement. Well, if if the force is mg sine theta along the plane, and we want to multiply that by the displacement along the plane, then x, then in this case of the plane, x, well, here's the plane again. Like x does not equal h. That's where I'm going with this. It's not just h. I don't know if you think it is or not, but if here's our plane, and here's theta, here's h, right? And here's x, right? Then according to SOHCAHTOA, right, sine of theta equals h over x. The sine of the angle equals the opposite over the hypotenuse, right? There, and x is the hypotenuse in this case. It's the displacement along the plane. So therefore, x equals h over sine theta. I hope people are with, well, we'll see in a minute if this is what you got or not. Therefore, if we, method one, approach one, if we want the work done down the plane, if we want to multiply the component of force that is parallel to the actual displacement, then work will equal mg sine theta times h over sine theta, which means, wonderfully, the sine thetas cancel out, and we get that the work that gravity does along the plane is mgh. Now I'm going to go further. I don't know if that's what you said or not, and some of you may have known that from, I don't know if you knew it or if you found it, but I'm going to do one other approach before I go any further. But that's the answer. That, well, I mean, I'll plug in the numbers now. Sorry, I'll plug in the numbers. So if the work is mgh, where by h, I'm sorry, by h I mean the height that was given of that plane. In other words, the work equals 85 kilograms times the acceleration due to gravity, which is approximately 10 meters per second squared, times the h, the height. Oh yeah, now, I forgot that there was hints and stuff given upside down, so that might have helped you too. But the height is 11 meters, right? So this is 850 times 11. Like, yeah, so 9.3. 9.35 times 10 to the third joules. That's the work that gravity did to bring this thing down, and it's positive. The work that gravity did to bring the boulder down the ramp is 9.35 times 10 to the third joules. But approach number two that that's one way to see it. But did I call that approach number one? Yeah. Yeah, approach number one. I mean, approach number two then. If you use the other coordinate system, the horizontal vertical coordinate system, we could say that the force of gravity is straight down mg, right? But then if you want to multiply only components of force and displacement that are parallel with each other, if you take the full bodied force of gravity mg, you would take only the component of displacement that is parallel to that force. In other words, what I'm saying is this. It seems like the same thing, but I'm saying i.e. whether we multiply the displacement by a component of force parallel with displacement, or we multiply force by a component of displacement, which is parallel to force, by a component of displacement parallel to force. Either way, we get that the work done by gravity is m times g times h. This is the work done by gravity through any vertical displacement h. What is it? I'm just thinking for 1 second. Yeah, I'm going to say this one last final way, because I realize that's a little. I'm saying even if you apply the strict definition, if work equals force times displacement, and that is force times, and that's force magnitude times displacement magnitude times cosine of the angle between them. If we just apply the strict definition, note that the theta between mg and x in this case is not 33 degrees. It's 57 degrees. I'm just going to say that I'm saying it, if you just apply the strict definition and if you just do mg, how can I put this? If you do mg sine theta times the displacement, so sorry. If you just do mg times the displacement along x, and then multiply by the cosine of the angle between them, the cosine, you'll still get mgh. Notice that the cosine of the angle between mg and x, the angle between mg and x is not the 33 degrees. It's the complement of 33 degrees, because 33 degrees is an angle measured between the plane and the horizontal. But if you apply the strict definition of work, you want the angle between the vertical and the displacement. So it would be the complement, it would be cosine of the complement of 33 degrees, which is the same thing as the sine of 33 degrees. And that's why everything we just did worked. I don't know if that helps or makes it even more confusing, but the bottom line is I'm saying at the end of the day, we'll start getting, I know we're going to end soon, or at least for most of you, we're going to end soon. Well, anyway, the answer I get for this is, for the first homework problem, is 9.35 times 10 to the third joules. And the key thing the takeaway, since we're going to end soon, like that's the answer to the homework. But the key takeaway is from now on, you can always say that the work done by gravity I'll write it here. Right? The key takeaway is note, from now on, the work done by gravity depends only on vertical displacement. That's what we're really noticing here, is that if work equals the dot product of force times displacement, then the only component of your displacement that the force of gravity would ever care about is your up-down displacement, because gravity is always in the up-down axis, right? And that so the work done by gravity to get you from one place to another doesn't matter how you get there at all. It doesn't matter how circuitous or horizontal your route is. The work done by gravity only cares about how much you were vertically displaced, i.e. your height, right? So from now on, work is done by gravity is always the force of gravity, mg, times the height change, the vertical displacement, h, always from now on. Okay, that's like the takeaway of that. So now I'm going to do a little bit more. It's 105.25. All right, I'm going to do a little bit more. Okay, B, sorry. B, the force of friction between the boulder and the ramp is 70 newtons. Calculate the work done. Okay, all right. So now if there's friction exerted on the ramp, that the work is going to be negative because the friction necessarily goes in the opposite direction of displacement. So if you do cosine, it's now not going to be the cosine of 0 degrees, it'd be the cosine of 180 degrees, so to speak. Done by friction will be negative, no matter how you labeled your coordinate system. Will be negative. Specifically, and again, I'm not even worrying about the integrals from here on in this sheet. Like, you still have to know the definition of work is an integral, but in every one of these problems, the force term is going to come out of that integral. So I'm always just multiplying force times displacement. So the only intricacy of this whole sheet, or like these work things, is to deal with the angle. But okay, the friction acts along the plane. I'm going to skip the free body diagram right now. The friction is along the plane. So it's in the exact opposite direction of displacement. Like, again, like I just said, well, anyway, so the work done by friction will be the force of friction times the displacement. And if you like, times cosine of 180 degrees, if you see what I'm saying. So the force of friction here is 70 newtons. The displacement of the plane is literally 11 over the sine of 33, right? The same way we said that before. 11 meters over sine of 33. I hope that's clear. Like, because I'm saying H equals, I'm sorry. Because I'm saying that sine of 33 equals 11 over the displacement that we're looking for here. So we get approximately 1.41 times 10 to the third joules. That will be the work. I hope that makes sense. But it's negative because it's going in the opposite direction from the displacement. So that's B. Stop me if I'm going. Oh, wait, let me look in the chat. I'm going back and forth between the sheets. Oh, there is something in the chat. I'm sorry. Hold on. I'm sorry. Okay, wait. How do you... Oh, sorry. This was 10 minutes ago, this chat. I'm sorry. How do I get mg sine theta for the force? Oh, well, yeah. Oh, okay. Great. Someone asked a question, but then they answered their own question, but I'll repeat it. It's good. Someone asked, how did I get mg sine theta for the force? I'm a little confused. Is it because that's the only force that lies along the plane? Yes, exactly. Because I'm looking, so there's like 3 different ways I could have done this, but yes, like because whenever so great question, person in direct chat. And even if you now get it, like, yes, I'm acknowledging and telling everybody, like, the whole thing with work is it's a dot product. So what this homework right now is emphasizing is the dot product nature of work, that what you're trying to do, however you do it, whether you use cosines or something else, what you're always just trying to do is take the component of force that is parallel with the displacement, or equivalently, you're trying to take the component of displacement that's parallel to force. What we kind of just showed there a minute ago, I did it kind of fast and spazzily, but what I'm trying to say is that's the same thing. like whichever is easier to do, we're looking at the scalar product between force and displacement. So we're only looking at the components that match. What we're really arguing again is it's like, well, even in this case, we're arguing that gravity is pulling straight down all the time, but the object is moving on a slant. So the effect of gravity on the object, the effect of gravity work-wise is just the effect of gravity on the downward motion of the object. Like gravity is still having an effect on the perpendicular axis, but that effect is to keep the object attached to the plane. Like the other component of gravity, mg cosine theta, is just balancing or counteracting the normal force. So some of gravity's efforts or some of the gravitational force is literally just keeping the object attached to the plane. But the rest of gravity's efforts, mg sine theta, are actually sending it along the plane. And that's the component of gravity that's doing work. So yes, I mean, that's a resounding yes to the person in direct chat. And I'm saying to everybody, like work is force times displacement, but only the components of force and displacement that match with each other, that are parallel with each other. The rest of any force is like not devoted to work. But since multiplication is commutative, you can look at it either way you want. You can either say the component of force that's parallel to the displacement, if you tilt your head one way, or you could say the component of displacement that's parallel to force. And in the end of the day, that's what I'm sort of showing in a spazzy way is in the case of gravity, it's easiest just to realize, oh, gravity, the force is always purely vertical. So the only component of the displacement that we need is the vertical component of displacement. So, okay, I'm saying this way too long, but it was really a great question. My initial look was to say the component of gravity that we need is the mg sine theta component, because that's matching with the displacement. And then we got that the displacement itself, interestingly, was h over sine theta. So then the sine thetas cancel out, and we're left with mgh, which really makes sense because it's just saying, oh yeah. Instead of saying the part of force that matched with displacement, we could have said the part of displacement that matches with force. The force is straight up and down, so it's just being multiplied by the straight up and down component of the displacement. I mean, I think the person who asked this now gets that. I'm not, but hopefully that's what we just found out. Okay, cool. Oh, and then there's someone else in the chat, and so that was a great question though in the chat. And you should submit for points, blah, blah, blah. So work done by friction. Now, yeah. Okay, so now to Josephine's public question, thank you for going public. Yes. I mean, the answer to Josephine's question is the work done by friction does directly automatically depend only on, depends on the display. I don't know if I'd call it horizontal, but depends on the full. Oh, I see. You're calling it horizontal because I'm calling it X. I guess that's maybe deceptive, but the hypotenuse, it only depends on the displacement along the plane. Two reasons for that. I mean, one, that is the displacement. So the work done, we would only want to count that component. But yes, unlike gravity, that's where friction's already acting. Like friction's a contact force. So in the free body diagram, I guess I should do this, and then here's the free body diagram. What's happening? Like mg is pulling fully down, so it has two components that it's doing. But the friction, the friction itself is coming from the plane. It's like from the object rubbing along the plane. So friction, we're not like, if we're in this coordinate system, we don't have to break up friction at all. It already is fully acting on the plane. None of friction is being wasted. I mean, it's all negative, but none of the force of friction is doing anything but going straight into the object. Okay, I don't know if that's clear. And because because I said we would end early, and we will, like in one, I'll write one English sentence, and obviously we'll pick up on this in 2 days. And there's obviously more to go over, but every time I say the component of force which does work, like the component that's not being wasted, like in this case, the mg sine theta component of gravity is the component doing work. The other component isn't. What am I really saying? That how can you visually picture what I'm saying? What I'm really saying is the component of force which does work is the component which transfers energy. That now we haven't solved those questions yet in the homework. But what I am saying is the sine theta component of gravity is what's giving kinetic energy, giving speed to the ball. The other component is doing something, but it ain't giving any energy to the ball. Like that's the point of this whole picture. But okay, what I'm going to say right now is I'm not going to go anywhere. But if you've done the course evaluation already, please have a nice night. And if you've done the homework, like you have nothing more to do. If you have other old homework to catch up on the old homework, blah, blah. If you haven't done the course evaluation, could you just hang up? I'm gonna stop the recording and all that. But if you haven't done the course evaluation, please hang out and do it. And if you need me to tell you where the link is, I will. But shut up. But please do the course evaluation is the point. Okay. Thank you guys so much. Okay, yeah, if you submitted already, then go. And again, it's not, I don't know. It's just the data is more important than anybody realizes. It really is. Like, it's your one chance to make a difference in like how the school is run. So anyway, okay, but thank you. Yes, and I'm turning off the recording.